Hello everyone, so welcome to my channel. So I was teaching thermodynamics in my last video. If you have not watched that, please go to my playlist thermodynamics and do watch my previous lectures. In order to understand my today's class, you have to read those lectures, my previous lectures. So in my last lecture, I was discussing about the expression of Cp minus Cv, that is constant pressure molar heat capacity and constant volume molar heat capacity, Cp and Cv. So I was discussing the expression of the mathematical expression of Cp minus Cv. I have derived it for ideal gas and also I have derived it for water at 4 degrees centigrade in my last video. So today I will continue my discussion on Cp minus Cv. I'll derive it for a gas obeying VanderWaals gas equation, and also I will derive it for in terms of alpha and beta. So let's start today's lecture. Let me share the screen. So if you have not watched my previous lecture, please do watch that, where I have derived the expression for Cp minus Cv. Here I am not deriving it, I am directly writing the mathematical expression. Okay, so Cp minus Cv is equals to T del P del T V into del V del T P. Okay, so I had already derived this. I'm directly writing this over here. So before I go to VanderWaals gas, because it is a little tricky, a little complex. So before going into that, I will derive it for a real gas obeying a little easy equation. Okay, so I will derive the expression for real gas obeying a gas equation. P V minus B is equals to RT. Okay, so this is simple. P V minus B is equals to RT. So what will be P? P is equals to RT by V minus B. So if I differentiate P with respect to T at constant volume, this will be R by V minus B. Okay, so I am differentiating with respect to T, so this will be 1 and V is constant. Okay, so I hope you understand these basic differentiations, and these are all basic mathematics. I hope you do understand that. If you do not understand, please let me know in the comment section. I will make a separate video on these basic mathematical rules. Okay, so again I can write it. PV minus PB is equals to RT. So what will be V? V is equals to RT plus PB divided by P. So this is RT by P plus B. So if I differentiate with respect to T at constant pressure, what will be this? So R by P, because this T will be 1 and this constant differentiation is 0. So we have got all these two. Now I will put it over the expression of Cp minus Cv. Okay, so what is the expression of Cp minus Cv? This is T into R by P minus B into R by P. So RT by P minus B into P into R. So again we can cancel this term because PV minus B is equals to RT. This was the gas equation. So we can cancel these two terms. So Cp minus Cv is equal to R. It was also R for ideal gas and also for a real gas. Obeying the gas equation, PV minus B equals to RT, Cp minus Cv is equals to R. Okay. So now let's derive it for VanderWaals gas. So a gas, real gas, obeying VanderWaals gas equation. Okay, so you will derive Cp minus Cv for VanderWaals gas. So what is the equation? P plus A by V square into V minus V is equals to RT, where A and B are the gas constants. Okay, so we can write it from here. P is equals to RT by V minus B minus A over V square. Okay, so now we will differentiate P with respect to T at constant volume. What will be this? R by V minus B, because differentiation of T will be 1 and this is constant, and this will be 0 because we have taken volume constant, so this is a constant term, so differentiation will be 0. And now we can again write it from here. We'll just multiply the both sides, so PV minus PB plus A by V minus AB by V square is equals to RT. Okay, so now AB by V square, this is a very small term because AB, they are gas constant, and B has a very large value. V has a very large value compared to A or B. So we can ignore this term because this is very, very small. So we can write PV minus PB plus A by V is equals to RT. Okay, so now we will differentiate both sides. Differentiation on both sides. So what will be that? P into del V del T P minus A by V square del V del T P will be equals to R. This will be 0 because P is constant, B is constant, differentiation of a constant is 0. Okay, so what will be the value of del V del T P? We can take this in common, so this will be P minus A by V square is equals to R. So we can write del V del T P is equals to R by P minus A by V square. Okay, now what do I know? Like from the expression of Cp minus Cv, this is equals to T del P del T P into del V del T P. So I'll just write it over here, which I got it from here, this value and this value. So this will be equals to, it was R by V minus V into P minus A by V square. Okay, so this will be R square T to B minus B, P minus A by P square. So now this will be R square T. Let me write this with a little trick. So B minus B to P plus A over B square minus 2A over B square. Okay. So now we can write this P plus A by P square from the VanderWaal gas equation. What was that which I wrote in the very beginning? P plus A by P square into B minus B is equals to RT. This is the VanderWaal gas equation. So we can write P plus A by P square is equals to RT over B minus B. So we'll just write this over here is equals to R squared T by B minus B RT over B minus B 2A by B square. Okay. So now we will take this in common. So R squared T by B minus B to RT by B minus B. We'll take this in common. So we can write 1 minus 2A to B minus B by RT B square. Okay. So now we can cancel this term, and also we can cancel this over here R and T. So this will be equal to, let me write in the next page, Cp minus Cv is equals to, what was that? R by 1 minus 2A B minus B over RT B square. So now we will assume that P minus B is equals to V, because B is very greater than B, so we can just take this assumption. We will take P minus B as V. So we can write it over here, R by 1 minus 2A by RTV, because we are cancelling this P minus B and V. We are taking P minus B as V. Okay, so we can write it R into 1 minus 2A over RTV or minus 1. So now we will use Mclaren series. What is that? 1 minus x to the power minus 1 is equals to 1 plus x square by factorial 2 by x cubed by factorial 3 plus up to infinity. Okay, this is the series. So in that case, if x is very small, we can ignore these terms. Later on, these terms we can ignore. We can write 1 minus x to the power minus 1 is equals to 1 plus x. So we'll do the same thing over here. This is a very small term. So because B, R and T, they have very large value, and A is a very small correction factor. So this value is very small. So we can do the similar approximation. We can use this Mclaren series approximation over here. So this will be equal to 1 plus x, that is 1 plus 2a over r t v. Okay, so then this is equals to r plus 2a over t v. So now we will again take another approximation, that we will replace this v using ideal gas equation. PV is equals to RT. This is another approximation. Okay, so we are doing this for VanderWaals gas, but we are replacing this V using our ideal gas equation. P is equals to RT by P. So we'll put it over here. So we can write R plus 2A by T into RT by P. So this is equals to R plus 2AP by RT square. So this is the mathematical value of Cp minus Cv for a real gas obeying VanderWaals gas equation. Okay, so now we'll do one more thing. We will derive Cp minus Cv mathematical expression in terms of alpha and beta. Okay, so let me write what is alpha and beta. So alpha is the thermal expansion coefficient. So alpha is the thermal expansion coefficient. This is denoted as 1 by V del V del T at constant pressure. Okay, and what is beta? Beta is the coefficient of compressibility. Okay, let me write this. This is coefficient of compressibility. So this is equals to minus 1 by V del V del P at constant temperature. Okay, so now we will derive Cp minus Cv in terms of alpha and beta. So we can write alpha by beta. What will be that? We can write it over here, 1 by V del T P times minus 1 by V del P del V constant temperature. We can cancel these two. So we can write del V minus del V del T P. We can just reverse this. So del P del V T. Okay. Now we all know that V is a function of temperature and pressure. Okay, so and all these are state function and perfectly differential quantity. So I had already discussed all these terms, state function, perfectly differential quantity, and cyclic rule in my first lecture of thermodynamics. Please do watch that to know the details on this. I'm not going into details. So I have also discussed about the cyclic rule over here. So I will use the cyclic rule for this. So I'm directly writing the cyclic rule. I'm not going into details. I'm directly writing that. Okay, so I will use the cyclic rule over here. Cyclic rule. So if you want to understand all these, what is cyclic rule, state function, and perfectly differential quantity, please do watch my thermodynamics lecture 1. Okay. So the cyclic rule will be del V del T P del T del P P del P del V at constant temperature this is equals to -1. So what we can write from here, del V del T P to del V del P del V T is equals to -1 by del T del P V. Okay, so alpha by beta, we will use this expression over here. So alpha by beta is equals to we have negative sign in both sides, so this will be cancelled, so it will be 1 by del P del T del P at constant volume. So we can write this as del P del T at constant volume. Now what is del V del T P? What is that? I have already discussed this in the mathematical expression for alpha. So we will use this expression over here. So this is equals to alpha into V. So now we will write the mathematical expression for Cp minus Cv. So I'm writing what was Cp minus Cv was T into del P del T V into del V del T at constant pressure. So I have already derived these two terms in my previous slide. So I can directly write it over here, alpha by beta and alpha V. So T into alpha by beta into alpha V. So what is Cp minus Cv? This will be alpha square T V by beta. So sorry, this is alpha square TV by beta. Okay, so this is the Cp minus Cv in terms of alpha and beta. This is a very important mathematical expression in thermodynamics. So please practice doing this. Okay, and we use this relation in many cases, so we have to remember this relation. Okay. So we have finished Cp minus Cv for ideal gas, real gas, for water at 4 degree, and finally in terms of alpha and beta. So before I finish, I would like to discuss a small thing, that is thermodynamic equation of state. Thermodynamic equation of state. So there are many thermodynamic equation of state. I'm just writing one of them. So this is P plus del U del V T is equals to T del P del T at constant volume. Okay. So this is one of the thermodynamic equation of state. So the one reason I have written it over here is that I would like to derive the mathematical expression of del U del V T. So this is a very important term. We have used it multiple times in case of thermodynamics first law. If you have not watched my video on thermodynamics first law, please do watch that. So this is a very important term, which is used in thermodynamics first law. So I will derive the expression of del U del Vt for ideal gas and for real gas. This is very simple. So I will just do it very quickly. So what is the ideal gas equation? So first do it for ideal gas. So ideal gas equation is PV is equals to nRT for n moles gas. So we can write P is equals to R nRT by V. So now we will do the differentiation of P with respect to T at constant volume. So what will be that? nR by V. So we'll just use this in this thermodynamic equation of state. So P plus del U del V at constant temperature, this is equals to T. We have just derived it, so into nR over V. Okay, so what is this? nRT by V, this is again P, so we can write it P. So you can see that we have P in both sides, so we can cancel it. So what is the value of del U del V T? Constant T, this is equals to 0 in case of ideal gas. Okay, and for Vanderwaals gas, what is the Vanderwaals gas equation? P plus A in square over P square to minus NB is equals to nRT. So what is the value of P? P is equals to nRT over V minus NB minus A in square over B square. So now you will differentiate with respect to T at constant volume. What will be that? nR by V minus NB. This term will be 0 because these are all constant. Okay, so again we will put this on the thermodynamic equation of state. So we can write what was the thermodynamic equation of state. So P plus del U del V T is equals to T del P del T V. So or del U del V T equals to T del P del T at constant volume minus P. So we will use this expression over here. So this is equals to T nR by V minus NB into T minus P. So now what is this? nR by nRT by V minus NB. So nRT by V minus NB is equals to P plus A n square by V square. We can see it from here. nRT by V minus B is equals to P plus A n square by V square. So I'm writing it over here. Okay. So now P will cancel. So what is the value of del U del V T? This is equals to A n square by V square for Vanderwaals gas. And this will be always be a positive quantity. So we can write that for isothermal expansion of a Vanderwaals gas, it leads to the increase in internal energy. For isothermal expansion. Okay, so what is isothermal expansion? Because T is constant, we can write isothermal, and expansion means V is being increased. So if V is being increased, it leads to an increase in the internal energy for a gas obeying Vanderwaals gas equation. Okay, so we can conclude this from here. So guys, I have derived the expression of Cp minus Cv for ideal gas, real gas in terms of alpha and beta. Also, I have derived this del U del Vt. So this is enough for today. I will discuss more on thermodynamics in my next videos. Please do like, share and subscribe. And if you have any question, if you do not understand anything, please write in the comment section. so that I can answer to your queries. So bye bye for today.